This lesson is being recorded, so if you do not feel comfortable talking during the lesson, please just send me a chat message and I can try to answer your question then. So what we're going over today is heat. So chapter 14, 1 and 2, we're talking about heat, and heat and temperature are different. Heat is exchanged. Temperature is something an object has. So temperature can describe, and heat is given between two things. So you give heat or you gain heat, that increases or decreases your temperature. So the amount of heat that you gain or give is going to change your temperature. It's like love. You can't be love, but you can give and receive love. Same kind of idea with heat. So the definition of heat is the spontaneous transfer of energy. And we talked about this last time with the molecules inside this here soda, right inside the soda. There are a bunch of molecules in there, and they're all moving around at different velocities. Same thing over here. Now, which one are moving slower, the ice or the soft drink?
The ice.
The ice, good. So when you bring them together, these faster moving molecules are going to collide with the slower moving molecules, and they're going to all even out and be the same temperature, which we like to call thermal equilibrium. They equal out at thermal equilibrium. That's when the temperatures are equal. So they're going to give the energy. The ones with extra energy, the high kinetic energy, the high temperature, give their energy to the lower ones through the collisions. Kind of like if two people are running, if one's running fast and the other one's running slow and they collide, they don't both go faster. They both tend to go to the middle speed between the two. You can also change the temperature by doing work. So remember, work is delta K and delta Q as well. We're going to learn Q as a symbol for heat. So work can be the change in Q, the change in heat energy. Work can be done. So that's mechanical. 1,000 kilocalories is 4,186 joules. So a lot of times, like on packaging, you'll see a capital calorie, 1 calorie, or let's say 9 calories. That's a kilocalorie. So a lowercase calorie is 4.186 joules. This is a really small unit of heat, a lowercase calorie. And you'll use that in like chemistry. So heat transfers for 3 reasons. The change in the temperature, right? If you have a difference in temperature, heat will change. If the masses are different, heat will change. So if you have a big, like if you're trying to cool down a whole cooler of sodas, you got to put more than a couple pieces of ice. You got to put 40 pounds of ice in there. So the mass matters and the substance matters. So it's a lot harder to change the temperature of water than it is to change the temperature of metal. So if you have a pot of water and you put a gas, you put a pot of water on the stove and apply heat to it, it takes a while for the water to boil, which is 212 Fahrenheit. If you lay a fork on the stove and you add the same amount of heat to the fork's going to get hotter a lot faster because of the metal. So the substance, and that gives us our formula for heat. Q equals mc delta T. Q equals mc delta T. The symbol C stands for specific heat. That's key. You probably didn't notice that in the little readings there, but the symbol C stands for specific heat. And your specific heat is how easily you change your temperature. The higher the specific heat, the harder it is to change your temperature. So Q equals mc delta T, right? We got to be in kilograms. This is joules per kilogram Celsius. Oops, excuse me, joules per kilogram Celsius. I wrote that wrong. And the temperature here has to be in Celsius. So make sure you got the right units. Here's the definition of specific heat. The specific heat is the amount of heat necessary to change the temperature of 1 kilogram mass, right? That's 2.2 pounds. 2.2 pounds. So that's a lot of water, right? That's like, what is it? 5 gallons of water is 45 pounds. It's like 9 pounds a gallon. So a quarter gallon of water by 1 degree Celsius. So that's not much of a change. So you have to put a lot of heat in to change the temperature of water by 1 degree Celsius. A lot of energy. All right, and that's what we're talking about. Here is a heat capacity specific heat scale. Notice the units here. This is the one we'll mostly use, joules per kilogram Celsius. Maybe on a quiz, they might try to trick you with a kilogram kilocal, kilogram Celsius. But normally we use the column over here. And we'll refer to this chart as we go through today's lesson because I don't have all these memorized. All right, first problem. A 15-gram piece of aluminum at 30 degrees Celsius gains 800 joules of heat. What's its final temperature? So let's write down what we have. We have aluminum, so let's go back to our chart. C for aluminum, 900 joules per kilogram Celsius. The initial temperature is 30 degrees Celsius. Q is 800 joules, and the mass is 15 times 10 to the minus third kilograms. Our formula, Q equals MC delta T. Q over MC equals delta T. T minus T naught equals Q over MC. So T equals Q over MC plus T naught. That's 800 divided by 15 times 10 to the minus third times 900 plus 30. The final temperature equals 89.26 Celsius. Anybody have any questions there? Anybody? All right, let's try another one or learn some more. Now, calorimetry is the idea of heat exchange, and the hot is going to give as much energy to the cold, or the amount of heat the cold gains is equal to the amount of heat the hot lost. So thermal equilibrium tells us that the sum of the Q's equals 0. So you could have 55 items, you could have 3 items, 2 items, whatever, but when you add all the items together, the heat gained has to equal to the heat lost. You can't, the heat just doesn't disappear. So it's kept in there. So this is the process of calorimetry. So these are kind of tricky, but we'll do the best we can to show you how to do this. So a 0.450 kilogram cup of coffee at 20 degrees Celsius is filled with 30 kilograms of brewed coffee at 95 degrees Celsius. The cup and the coffee come into thermal equilibrium at 80 degrees Celsius. If no heat is lost to the environment, what's the specific heat of the cup material? All right, so we have a cup and a coffee. So the heat of the coffee, which is essentially water, plus the heat of the cup equals 0. One gains, the other loses. So this is telling us the mass of the water times the specific heat of water times the change in temperature of the water plus the mass of the cup times the specific heat of the cup times the change in temperature of the cup equals 0. Do you follow me? Does anybody have anything to clarify? So let's see what our given is. We know the mass of the cup, 0.45 kilograms. The specific heat of the cup is what we're looking for. We know the temperature of the cup is 95 degrees Celsius. That's the initial temperature. We know the final temperature of the system is 80 degrees Celsius. Oh no, excuse me, the cup's 20 degrees. Got ahead of myself. It happens sometimes. You got to be careful out there. We know the mass of the water is 0.30 kilograms. That's our coffee inside the water. We know the temperature of the water is 95 degrees Celsius to begin. And I do know the specific heat of water, 4186 joules per kilogram Celsius. So now we want to find the specific heat of the cup. So our goal is to find the specific heat of the cup. So you want to do the algebra? Let's do the algebra. Mass of the cup, specific heat of the cup, delta C of the cup equals mass of the water, specific heat of the water, delta C of the water. I got mixed up. Delta T, I said delta C, I meant delta T of the water. So the specific heat of the cup equals the mass of the water, and this has to be negative because I took it to the other side. I subtracted it from both sides. Negative MW CW delta TW over MC delta TC.
Would T be time in this situation?
No, T is temperature. Big T is temperature. Big T is temperature. Little t is time. We're going to do a problem with time coming up. So the specific heat of the cup equals negative 0.3 times 4186 times 80 minus 95, and the negatives are going to cancel out, see, over 0.45 times 80 minus 20. What's the specific heat of the cup material? I got 697.67. Any questions there? Let's go see what the material's made out of. So it's roughly 700. Do we have anything close to 700? No. Have to look it up. Ceramic is probably close to 700. There's concrete at 840. Maybe it's styrofoam. We don't have styrofoam on here. I don't know what we're holding our coffee in. Anybody have any questions on how we did this? Anybody?
Nope.
Thanks.
Okay.
Thank you. Anybody else?
So I got here a little bit late, but just the subscripts of W means like what exactly here? Because it's like the first set have subscript W and the other half have subscript C.
W stood for water because the coffee is essentially water. And C stood for the material of the cup.
Okay. So then in other situations, is that subscript going to change, or did you just put that there just to like make it simpler for us to understand?
That subscript's just there to represent which variable we're dealing with. Yes, they're going to change every problem. Usually water's W, but most of the other ones will change. Glass has a specific heat around 700. Must be a glass mug. Any questions on this? Any other questions on this problem? All right, now, whew, we got a 3-bagger. We got 3 of them we're putting together. It says a student doing an experiment pours 0.25 kilograms of heated copper shot into a 0.46 kilogram aluminum calorimeter cup containing 0.15 kilograms of water. The mixture in the cup comes to a thermal equilibrium at 40 degrees Celsius. What's the initial temperature of the shot? So we're going to fill this chart in, and then you guys are going to do the math. All right, are you ready? A student pours 0.25 kilograms of heated copper shot. So that is 0.25 kilograms into a 0.46 aluminum cup. And it contains 0.15 kilograms of water. I don't need to write kilograms in there. I got it in the chart over here on the left, so I don't need to write it in every time. We know the specific heat of water is 4186. We'll go back at the end and look up the specific heat of the other two. The thermal equilibrium, the final temperature is 40. So they all have a final temperature of 40. And the water in the cup are at the same initial temperature of 25 degrees Celsius. So let's go back and find out what aluminum and copper. Copper is, oh boy, I can't even see what I wrote here. Copper is 387 and aluminum's 900. All right, so this is what, 387 and 900. So I want you guys at your seats to find out TC, the temperature of the copper. We'll call this guy TA, and this would be TW, right? So this would be MA or MC, MA, MW, CC, CA, CW. Give this one a shot. See how you do. Anybody have any questions? Just shout at me.
I got an answer, but 50-50, I think.
All right, somebody's got an answer. That means I can start solving. Sum of the Q's equals 0. 50-50. I hope it's better than 50-50. So that means QC plus QA plus QW equals 0. Our goal is to find TC. So MC, I wish I had an undo button, but I just don't. I got to erase it every time. MCCC delta TC plus MACA delta TA plus MWCW delta TW equals 0. So let's go through here, and we got to get we got to get CC by itself, or TC. This is the one we're trying to isolate. So what we do is delta TC equals negative MA CA delta TA minus MW CW delta TW over MC CC. So delta TC equals, let's see if I can fit this here. It's going to take all my skill. Negative 0.46 times. No, that's Z. Sorry. Yeah, 0.46 times 900 times negative 15 minus 0.15 times 4186 times negative 15 over 0.25 times 387. So delta TC equals dun, 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 dun. $161.53. That's the change in temperature. Is that what you guys got?
That's what I got.
Nice. So that
Wouldn't the water-
means
Sorry.
we're looking for TC. So remember, T minus TC equals 161.53. The final temperature is 40 minus TC equals 161.53. This is actually comes out to be negative. This should be a negative temperature change. Sorry. When you do this math here, those are positive 15s. Yeah, be 40 minus 25. I screwed that up. Positive 15s. So that means this is negative. This is negative. So TC ends up being 201.53 degrees Celsius. That's how hot the shot is. Does that make sense?
Yep.
Nice.
I forgot how to add. That was my only problem. It's always the easiest stuff.
It's all, yeah, I did too. I took 40 minus 25 and came up with negative 15. I got a lot of pressure on me though. You know what I mean? You don't really have an excuse.
That's true.
Oh man. Anybody have any questions on that? You got to ask. It's the only way I'll ever know and be able to help. All right, here comes the next one. At what average rate would the heat have to be removed from 2.5 liters of mercury to reduce the liquid's temperature from 60 to its freezing point in 5 minutes? Dang. I don't have the chart for freezing point of mercury. I got to look that up. I'm going to get my book out. So I'll be paging through this book. So our goal here is past it. Here we go. I'm going to write down the specific heat of mercury is 139. Found that in the book. And then we got to find the melting or the freezing point of mercury. That's in the book too, on a different page. Mercury, negative 38.9. So the final temperature is negative 38.9. Now this isn't necessarily that's not right, a calorimetry problem. This is just a straight up heat exchange problem. So it probably would have been better served to put it earlier in the slides. But again, the concept is what I'm looking for here. I just made a mistake. I should have put it earlier. But anyway, it says at what average rate would heat have to be removed from 2.5 liters of mercury? So that's a volume, 2.5 liters, to reduce the liquid's temperature from the initial temperature of 60 degrees Celsius to its freezing point. So we're going to need another piece of information as well. What information is that going to be? I don't know if I can have that in the book. I'm going to have to look that up on the old interweb.
The density of the mercury.
Very good. We're going to need the density of the mercury, which that might be harder to find in this here book. I'll look up on the internet. Somebody look it up on the internet. Density of mercury in kilograms per meter cubed, or kilograms per meter cubed, or kilograms per liter. See who can find it first. Be the winner. Let me win in the book. Oh, I found it first. The density of mercury is 13.6. 13.6 kilograms per meter cubed. All right. Feels good to be a winner. Now, let's change that into liters, or we can change this into meters cubed. Either way. Remember our conversion, 1,000 liters per meter cubed. So that'd be 2.5 times 10 to the minus third meters cubed. Now, let's see what the question is asking. What average rate? What average rate? So that is the heat per unit time. Anytime you see rate, That means per unit time, whether it's velocity, displacement, energy, work, heat, right? The rate something is done is per unit time. So that's your power. So your power is, well, MC delta T over T, or excuse me, times, yeah, over T. Ugh. Does that make sense? So anyway, we're looking for the rate that it's done. We're looking for the power in this problem. So we're looking for Q over T. So what should our units be? What are the units of Q over T for this problem?
Watts.
Watts, good. That's a joule per second. So the power is equal to MC delta T over T. Remember, density equals mass over volume. So mass equals density times volume. So big P equals density times volume, C of mercury, delta T. Oh, no, it doesn't. I got this screwed up. Yeah, what am I doing? And our time, I forgot to write our time down. That's what screwed me up. 5 minutes, which is 300 seconds, right? 5 times 60. So our power is 13.6 times 2.5 times 10 to the minus third times 139 times 60 minus negative 38.9 all over 300. Forgot to bracket out here. I got 1.56 watts. Did I put that in right? Let me check. Let me double check. I might have put 1.36.
So wait, for the temperature, don't you subtract it or did you times it?
You gotta, well, delta T is the difference. So you take 60 minus 38 point or negative 38.9. So delta, oh, what am I doing here? I got erasing, looks garbage. Like, so so delta T equals 60 minus negative 38.9. So then you would take that and multiply it down there at the bottom. .56 watts or joules per second. Anybody have any questions on that? Did I screw something up? Did I get the density right? Oh, son of a gun. That's 13.6 times 10 to the third. In my race to be the first one done, I screwed that up. That's 13.6 thousand. Son of a gun. The chart got me. I got to redo my math here. It comes out to be then we'll just move it 3 decimal places, 1560 watts, right? There we go. That looks better. I thought that answer looked a little screwy. I screwed up this temperature too, jamming it in here. This problem and I just weren't friends today. Final is 38.9, so it's negative 38.9 minus 60. That's a negative 1560. Yuck. Should have done this earlier when I was fresh, before I got frazzled. Anybody have any questions on that?
Not about this. I'm sorry, I gotta be honest, I kinda came in a bit late. So, yeah.
I think he gone.
Yeah,
Was it
I
something
think-
said?
That's it. He's finally done with us.
I feel good now.
Rage quit. F in the chat.
Just
Yeah,
don't
after-
swear because it's still recording. We wouldn't want to have to re-record everything.
F.
Nah,
So does that mean we're good to go, or
I don't know.
nah,
I guess
don't-
we can wait for a bit. If he doesn't show back up, we can leave, I guess.
If teacher doesn't show up 15 minutes, leave class, guys.
well, if he doesn't show up in 15 minutes, then we wasted 15 minutes because class would be over anyway.
Oh, true.
Especially the whole quiz part.
We
Yeah.
could quiz each other.
At this point, he would probably have to give us all at least partial credit for at least showing up to class.
True.
True.
Either way, we're guaranteed at least half on a quiz, even if we don't get it. So
All I'm saying is if we all leave, he can't punish all of us.
Yeah, you could.
Yeah, you could. Yeah.
I mean, it's only
who
2
else is
points.
having fun with the
Uh,
buoyancy lab?
And he'll try.
When's that due again?
Today?
No.
I think it's
No,
next.
it's not.
It's a week from now.
Is it a week from now?
I figured it was a long
It's the
time. From now.
18th.
It's due Wednesday, like next Wednesday.
Oh, is
Yeah,
it next Wednesday? I thought it was this Wednesday.
No, it's due the 18th.
I asked,
Don't scare us like that.
Jesus Christ.
Okay,
I almost killed myself.
What do you think I've been doing all afternoon?
I couldn't
It's
message.
still recording.
I couldn't message you about. I was sleeping.
I figured you were at work.
No,
Be careful. He probably has all of our testimonies now. Just because it is
You
Testimony
think-
to
recording.
what?
But do you
Well,
think?
the only thing he has is testimonies, and I'm a hard worker.
Oh,
Well, good thing I won't have to work on that anymore, except the giant thing of Play-Doh I made is just gonna sit over
it
there.
actually has you making Play-Doh.
Yeah, you have to either
Oh
Play-Doh
my
or clay, and
what is it?
yeah,
Oh,
That
Like
is
you
not
gotta-
reasonable.
it's for testing buoyancy. Oh, he's back.
Hey, I'm back. I get kicked out. I was recording